Welcome to this explainer. Okay, I want you to close your eyes for just a second. Imagine you're standing on a sidewalk, right? You hear an ambulance approaching from down the street. The siren is high-pitched, it's urgent, piercing. But then, the exact moment it zooms past you, the pitch drops completely. It stretches into this lower, groaning wail. We've all heard it, we all know exactly what it sounds like. But how often do we actually stop to think about the hidden physics making that happen? Well, today, we're going to explore that very phenomenon. It's this fundamental principle of wave dynamics that doesn't just dictate how we hear passing sirens, but it's literally how we map the human bloodstream, how we predict deadly weather patterns, and even how we measure the expansion of the universe itself. Let's dive in.
So, here is our roadmap for today. We'll be looking at the siren's secret, the math behind the pitch, light waves break the rules, relativity and the redshift, and finally, we'll wrap up with from bloodstreams to galaxies.
All right, let's jump right into Section 1, the siren's secret, understanding the basic phenomenon.
Okay, so what's actually happening when that ambulance drives by? It all comes down to the Doppler effect. Technically speaking, this is the change in frequency or wavelength of a wave in relation to an observer who is moving relative to the wave source. But simply put, if a wave source is moving toward you, it squishes its waves together. For sound, more waves hitting your ear every second means a higher frequency, and your brain interprets that higher frequency as a higher pitch. Now, when the ambulance passes you and starts moving away, those exact same sound waves get stretched out. Fewer waves hit your ear per second, the frequency drops, and suddenly, you hear a noticeably lower pitch. The crazy thing is, the siren itself isn't changing its tune at all. It's your relative position to the moving siren that changes the tune you hear.
That brings us to Section 2, the math behind the pitch, calculating sound waves. Let's take a quick look under the hood at the actual mechanics here.
I want you to consider the number 331.3 meters per second. That is the baseline speed of sound in air at 0 degrees Celsius. But here is the absolutely critical thing you have to remember about sound. It is a mechanical wave. It requires a physical medium to travel through. We're talking air, water, or even a solid metal rod. And because it totally relies on that medium, the speed of sound can actually shift, depending on the properties of the medium itself, like its temperature or its density. But no matter the specific speed, the wave desperately needs that medium to push through.
And you know, that reliance on a medium creates a truly fascinating mathematical reality. When a sound source moves, the wave frequency changes based on the relative velocities of both the source and the observer. Just picture it. The sound source is literally pushing into the very sound waves it just created ahead of it, compressing them together. Meanwhile, it is basically running away from the sound waves it's leaving behind, stretching them way out. If you were just standing perfectly still, the speed of the wave through the air doesn't change one bit, but the frequency with which those squished or stretched waves actually hit you, that absolutely does change.
So this naturally leads to a pretty fun question. What actually happens when the source of the sound starts moving faster than the sound waves it's producing? To measure this, physicists use something called the Mach number. You find it simply by taking the velocity of the source and dividing it by the velocity of the wave. Pretty straightforward. So if you're traveling at exactly half the speed of sound, you're at Mach 0.5. But what happens when that fraction reaches exactly 1?
Well, Mach 1 is the sonic threshold. At this exact precise point, the source is moving at the exact same speed as the sound waves it is generating. Because of this, the sound waves physically cannot escape the source before the very next wave is emitted. So what do? They all stack up right on top of one another, building this immense, incredible pressure. When a jet breaks past this barrier and goes supersonic, it leaves that massive buildup of sound energy trailing behind it in a huge cone shape. And when that cone of compressed air finally washes over you down on the ground, you hear it as a massive, explosive shock wave, a sonic boom. It's literally the Doppler effect pushed to its absolute limit.
Okay, so we've got sound down. But now, it's time for a pretty major pivot. Let's move to Section 3, light waves break the rules. Sound versus light.
I want to pose a question directly to you. Think about this. How is the Doppler effect different for light compared to sound? We literally just established that mechanical waves, like sound, physically compress inside a medium. But here's the catch. Light does not behave like a traditional mechanical wave. Not at all.
Unlike sound, which absolutely needs that medium to travel, light waves are electromagnetic. They can travel perfectly fine through a total empty vacuum. But more importantly, and this is what Einstein famously established, the speed of light is a universal constant. It does not matter how fast you're moving toward a flashlight or how fast that flashlight is moving toward you, the speed of the light wave hitting your eye remains exactly, perfectly the same. So think about it. If the speed can't change, how on earth can there be a Doppler effect for light? The answer is that while the speed remains locked, the frequency and wavelength actually do change, but they do so because of the wild, mind-bending rules of relativity.
And that brilliantly illustrates why we need to jump into Section 4, Relativity and the Redshift, Cosmic Speed Traps. This is where the physics get truly cosmic.
Imagine a light source just tearing away from an observer at a massive, massive velocity. From the perspective of the observer, who's just standing there, they literally see the wave pattern stretched out over space and time. Because the speed of light is absolute and cannot change, the math literally requires us to stretch the wavelength to account for the relative motion of the source. When you apply the relativistic math here, the wavelength changes by a factor of 1 plus the velocity divided by the speed of light. Essentially, the faster the source is moving away from you, the more dramatically the light wave is stretched out.
So, what does a physically stretched light wave actually look like to the human eye? Or, say, to a giant telescope? Well, astronomers call it redshift and blueshift. When an object in deep space is moving away from us, the wavelength of its light stretches out. Now, in the visible light spectrum, red has the longest wavelength, so the object's light literally shifts toward the red end of the spectrum. Redshift. Conversely, if a star is racing right toward Earth, its light waves compress and they shift toward the shorter wavelengths. That's blueshift.
Let's look at a really concrete example of a cosmic speed trap using the actual equation from our sources. Suppose a distant galaxy is moving away from Earth at a frankly unbelievable speed, 82.5% the speed of light. Let's say it naturally emits a radio wave that is exactly 0.525 meters long. By plugging that velocity into our relativistic Doppler equation, we see that by the time that exact wave reaches us here on Earth, it is stretched way out to 1.70 meters. It is massively redshifted. And you know, this is exactly how astronomers figured out that the universe is actually expanding. Almost everything we look at in deep space is redshifted, meaning pretty much everything is flying away from us.
All right, we've been way out in the cosmos, but let's bring it all back home for Section 5, From Bloodstreams to Galaxies, Incredible Practical Applications. It's amazing, but this one single physical principle is incredibly diverse in everyday practice. In astronomy, like we just talked about, we track stellar movements. This even allows us to discover hidden exoplanets by watching the subtle blue shifts and red shifts of a star as a planet's gravity gently tugs on it. In meteorology, weather radar uses the Doppler effect by bouncing microwaves off water droplets in the air. By measuring the frequency shift of that returning signal, meteorologists can tell exactly which way the wind inside a cloud is blowing, which literally allows them to predict tornadoes before they touch down. And finally, there is medical imaging.
If we look specifically at medical ultrasound applications, the Doppler effect is quite literally saving lives every single day. Using high-frequency sound waves, facilities like Ultrascan Diagnostics use color Doppler imaging to safely peer right inside the human body without any invasive surgery. By measuring the tiny frequency shifts of sound bouncing off your moving red blood cells, doctors can visualize the exact speed and direction of your blood flow. This allows them to instantly detect life-threatening blood clots in the legs, assess the super intricate function of heart valves, and even monitor the healthy development of blood flow to a fetus during pregnancy.
So here is the absolute coolest takeaway from all of this. The exact same physical principles used by a technician in your local clinic to check your heartbeat are being used by meteorologists to track deadly supercell storms, and by astronomers to discover entirely new worlds orbiting distant stars. It is one single universal rule governing how waves interact with motion, and it scales absolutely flawlessly from the microscopic all the way to the galactic.
We'll end today with this fantastic quote directly from our sources. The Doppler effect is more than a scientific curiosity. It's a vital tool with applications ranging from healthcare to astronomy. I love this because it shows us that physics isn't just a bunch of numbers on a chalkboard. It is the literal hidden framework of our reality. So the next time you're walking down the street and you hear that ambulance siren wail and drop in pitch as it speeds by, ask yourself, what other invisible forces are shaping the universe around you, right in plain sight? Thanks so much for joining me on this explainer, and keep questioning the world around you.